I welcome you all to 12th Biennial National Conference of Physics Academy of Northeast. My name is Gyanraj Bora. The title of my work that I am going to present is Structural, Optical and Electrical Properties of Copper Oxide Nanostructures Prepared by Reactive DC Magnetron Sputtering, which is accomplished under the guidance of Dr. Bimal Kumar Sharma. Now let's move to the introduction part. Copper oxide is a transition metal oxide and has a monoclinic lattice structure as shown in this figure, and it is well known for its p-type conductivity and exhibit both indirect and direct band gaps depending on different process parameters. In recent years, copper oxide received special attention from many technological fields and scientific areas. And for examples, this oxide is considered an efficient catalyst, and copper oxide nanoparticles have been good sensing material and plays an important role in optoelectronics. Different applications of copper oxide nanoparticles in different fields are shown in this figure. Experimental procedure and characterization. Copper oxide nanostructures are deposited using reactive DC magnetron sputtering. A schematic diagram of DC magnetron sputtering is shown in this figure. The substrates are mounted, which is glass in this case, at a distance of 45 mm from the copper sputtering target fitted in one of the magnetron. The chamber is first evacuated by a rotary pump to a pressure of 2 Pascal, and the low pressure of the order of 10 to the minus 4 Pascal is created using an oil diffusion pump. A 99.99% pure copper target was sputtered in 84% argon and 16% oxygen plasma at 70 watt sputtering power at different pressures varying from 1 Pascal to 6 Pascal and different deposition time from 10 minutes to 60 minutes. The deposited films are characterized as in X-ray diffraction, field emission, scanning electron microscopy or FESM, UV visible absorption spectroscopy, 4-probe resistivity measurement, and Hall measurement. Technique. Now coming to the results and discussion part. Microstructural studies are done using X-ray diffraction technique, which reveals the oxide phase of the deposited nanostructures. Here, the XRD patterns of the film 10 minute, 40 minute and 60 minute at 6 Pascal sputtering pressure is shown and compared with the standard data of copper oxide. The XRD pattern matches with the standard copper oxide data and confirms the absence of other oxide phases in the nanostructure. No peak attributable to copper oxide are observed due to the very low content of copper oxide for the nanostructure deposited for 10 minutes. The crystallite size are calculated using Scherrer formula, and the nanostructure deposited 40 minute and 60 minute has crystallite size of 13 and 26 nanometer respectively. Field emission scanning electron microscopy is used to analyze the morphologies of the nanostructures. As observed in this figure, isolated nanograins of copper oxide are observed in nanostructures that have been deposited for 10 minutes. But when the deposition time is extended to 40 minutes, nearly film-like structure is observed. Sputtering pressure of 8 Pascal produce highly isolated nanograins, and lowering the pressure results in less isolated nanograins. The Thickness of the films are calculated using cross-sectional FESM images using image software, and the thickness of the film deposited for 60 minutes is 140 nanometer. Optical studies. UV visible absorption spectroscopy is used for optical studies, and transmittance and absorbance spectra are recorded in the range 200 to 1100 nanometer. In this figure, the variation of sputtering pressure for absorbance is shown, and this is the enlarged version of this figure. The nanostructures absorb light strongly in the range 280 to 400 nanometer region, and it is observed that the absorption capacity increased in the visible region with the decrease in sputtering pressure and increase in deposition time. And as shown in this figure, the variation in deposition time, and this is the enlarged version of this figure. The nanostructures have transmittance more than 80% in the wavelength range 780 to 1100 nanometer. Electrical properties. In electrical properties, seat resistance is measured using four-probe resistivity measurement, and carrier concentration is calculated by using Van der Waals technique. With decreasing sputtering pressure, seat resistance decreases, as shown in this figure, and also with increase in deposition time, seat resistance decreases, which is clearly observed in this figure. Hall measurement confirms p-type conductivity of the deposited nanostructures. The seat carrier concentration is found of the order of 10 to the power 12 and 10 to the power 13 per centimeter square for the films 40 minutes and 60 minutes respectively. In conclusion, copper oxide is successfully deposited using reactive DC magnetron sputtering. XRD pattern confirms absence of other oxide phases. Hall measurement confirms p-type conductivity. And the deposited nanostructures might be combined with other metal semiconductors to form efficient heterostructures and PN junctions for possible application in photodetection and photocatalysis. And finally, thank you all.